So welcome to part 2 of lecture 10. In part 1, I introduced the null space of a linear transformation, and we saw that the null space was a subset of V. But what we're actually going to do in this part is we're actually going to show is that the null space has more structure. It actually has the structure of a vector space itself. In fact, it is an example of a subspace of the vector space V. So to prove this, we need to just check the 3 subspace conditions. Right, so, and I thought I would actually write out all of them so we could see this in kind of in detail. So is the 0 vector inside of the null space of T? Right, well, why is that? Well, the 0 element is in the null space since all linear maps satisfy T sends 0 to 0. Okay, so every linear map has the property that takes 0 to 0. Now, 2, what else do we know? Well, we have the property that if we take 2 vectors u and v in the null space of T, then what we want to do is we want to show that the sum of these 2 vectors is also in the null space, right? Well, then if I look at what happens when I plug u plus v into my linear transformation, by the additivity property of a linear map, we can break this up. So this is by the additivity property. And now we know that Tu is equal to 0, and we know that Tv is equal to 0, right? And that follows since u and v are in the null space of T. And finally, 0 plus 0 is equal to 0, right? So we actually get that the sum of u plus v is in the null space of T. Okay, so definitely the null space is closed under the the operation of addition. And so the last thing we have to do is check to see if the null space is closed under the operation of scalar multiplication. So let's take u in the null space of T, and let's take some arbitrary constant lambda inside of my field F. Then we know that T evaluated at lambda u is the same thing as lambda times Tu, and this is by the homogeneity property of linear maps. Now, since u is in the null space of T, we have that Tu is equal to 0. So if we put all the pieces together, what we have is the following, is that T evaluated at lambda u is lambda times Tu, which is equal to lambda times 0. So this is the 0 vector times the scalar, and this is equal to 0. So lambda u is also in the null space of T. So we've shown that 0 is in my space. We've shown that the null space is closed under addition, and we've shown that the null space is closed under scalar multiplication. So this verifies that the null space is a subspace of my vector space V. Okay, so what else can we do with this? Okay, well, now that we know what a null space is, I just want to talk briefly about what it means for a function to be injective. So a function t from v to w is injective, and some books call it one-to-one, and I may actually flip-flop between the two terms. If whenever tu is equal to tv, so if I have 2 vectors u and v in the big space V, and they both get mapped to the same w, that means that they had to have been the same to begin with. Okay, and one of the reasons we like the null space is somehow it measures injectivity. Now, what do I mean by measures injectivity? Well, the following theorem kind of captures this idea, is that we can tell whether a function is injective, okay, a linear map is injective, by the size of the null space of the linear transformation. Okay, so it says that the null space will be only the 0 subspace if and only if T was an injective linear map. So let's go through a proof of this. Okay, so we're assuming that the null space only contains the 0 element, and we want to show that our function is injective. Right, so we want to suppose that tu is equal to dv, and what we want to show is that u is equal to v. Okay. Well, what can we say here? Well, if we assume this, we can rearrange the equation, so we get that tu minus tv equals 0. But t is a linear map, so tu minus tv is equal to the same thing as t evaluated at u minus v. So tu minus v equals 0, right? Because this term is equal to this term, which is equal to 0, implies that u minus v is in the null space of t, because u minus v gets sent to 0 by t. But this contains only the 0 element, right? So this means that u minus v is equal to 0, which is another way of saying that u is equal to v. Okay, so we've shown that if u and v get sent to the same element, they had to have been the same to begin with, provided that the null space is equal to 0. Okay, now let's do the reverse direction. Let's suppose that it's injective, and now we're going to show that the null space only contains the 0 element. Okay, so let t be injective, and suppose that u is in the null space. Okay, so i.e. u gets sent to 0. What else can we say with that? Okay, well, we also know that t0 is equal to 0 for any linear transformation, for any linear map. So any linear map always sends 0 to 0. Okay. Now, since t is injective and because tu is equal to t0 and they both equal to 0, this means that the vector u had to be the same as 0. So the null space of t, which contains all the u such that tu is equal to 0, we said that if you have something in this set, it actually has to be the 0 element. So the null space is just contains the element 0. So that's one of the reasons we like the null space. It's kind of a measure of the injectivity of your linear map. So in the next part, we'll talk about another subspace that we can get from a linear map. I'll see you there in a couple minutes.